Chapter 2: Limits and Continuities. Objectives: interpret the rate of change at an instant in terms of average rates of change over intervals containing that instant. Represent limits analytically using correct notation. Interpret limits expressed in analytic notation. Show that for a function f, the limit of f of x as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c, but not equal to c. If the limit exists and is a real number, then show that the limit can be expressed in multiple ways, including graphically, numerically, and analytically. The average speed. When f of t measures the distance traveled at time t, where time t is the difference between t2 and t1. The distance traveled at time t, which is also mentioned here as distance traveled, is from f of t2 to f of t1. When we subtract f of t1 from f of t2 will give us the distance traveled, and the elapsed time is t, and t is given by t2 minus t1. So if we divide the distance traveled by the elapsed time, it will give us the average speed. Average speed. For studying the limits, let's start with a simple experiment. Now we have a ball over here, and this ball we want to drop it. And when we drop it after 0.0001 time, the ball will have an average speed of 32.0016, and after 0.001 time, the ball will have traveled by the speed of 32 on the average 32.016 all the way until when the time from the ball dropping until this moment was 1 time unit, then its average speed would be 48. So let's take a look at the ball now. It is falling, and then we will evaluate the rest. Now the ball fell. Now let's take a look at how we can compute the average speed for each of these intervals. Each one of these is an interval. This is an interval, first interval, this is the second, third, fourth, and this is the last interval. So let's take a look at how we can find the average speed. It's given by an equation. This is the equation. And it has 16. 16 has to do with the gravity, because this is a free fall. Free fall means there is nothing except the gravity that's going to impact how fast the ball is going to fall. There is no wind, there is nothing. So 16 multiplied by t0, the time the ball is dropped, and h is the time that the ball kept falling. So h is going to take from 0.00001 all the way until 1. So travel time, we can put here h. So these are values for h. How are we going to do it? We have to look at, for example, when h is equal to 1. We're going to go with h equal to 1. It all applies for all of them, but it's easy to do h equal to 1. When h is equal to 1, we also assume that at t0 is equal to 1. So we're going to go ahead and plug on this equation. To plug on this equation, t0 equal to 1 and h equal to 1, this is what we're going to have: 16 multiplied by 1 plus 1 square, and that's minus 16 multiplied by 1 square, because this is the second part. and this is going to be equal to 64 minus 16 divided by 1, and that's equal to 48, which is this case. So when the ball travels for like 1 time unit, its speed will be 48. You can see that the speed is increasing. Why? Because the ball is falling, and at the moment the ball is released, is just within that much time, the ball is going to maintain around 32.001 average speed, and then the speed will continue to increase until this point. So that much about it. Let's go ahead and a real example. Here is an example, and here is pretty much the short time, and here is the equation that we just discussed, and delta y is the time, delta y is the distance that the ball fell, and delta t is the time it took it to fall, and here are the values of h in decreasing or in increasing order, and here is the value of the average speed in increasing order for t equal to 1, and this is for t equal to 2. Here is an example, and this example about f of x is the hypotenuse, and what we want is we want to know what is the limit of f of x, that means the limit of the hypotenuse as x goes to 0. We want to set x to 0. These are the values for x. So x starts from 11, and we want to get x to drop all the way to 0, as if we are taking the limit until it goes to 0. And here is the equations for the hypo. So this is the equation for the hypo. Let's take a look at x, where x is one of the, it's like the adjacent. It's going to be adjacent to the right angle. So let's take a look at the triangle. There is a triangle, and over here it is 4. The height is 4, and over here this is adjacent, so adjacent is 11. So if we want the hypo, it's going to be 4 square, which is 16, plus 121, which is 11 square, and we get a square root, we get the length of this hypo. Now what we want is, this is our x-axis, so we want to decrease 11. We want x to be going until 0. If x reaches 0, that means there will be no triangle, there will be a straight angle. So we're just saying limit as x approaches 0. We're not gonna take it all the way to 0, because if you take it all the way to 0, the length of the hypo is going to be the same as the length of this height, and there will be no triangle. So we're just going to do limit only. And if we do the limit, before we proceed, we're going to go step by step and shrink the hypo step by step. Let's say the next step, instead of 11, we will get to 8. So now the adjacent is 8, and since it is 8, the hypo is going to be 4 square, which is 16, plus 8 square, 64, and the square root will give us. And this is this case where this is 8, and we can continue this way. Next, the value is going to be 5, so we're going to go ahead and reduce the adjacent, because x is moving towards 0. X moved from 11 to 8, and now it will move to 5. So let's go ahead. Now x moves to 5, so this is only 5, and for that the hypo will be 16 plus 25, the square root of the sum, which is this case. And then the next case is 3, so x will continue, so this is going to result in the adjacent equal to 3, and for that matter the hypo will be the square root of 16 plus 9. Now if we moved to 0, like I said, we're not going to get a triangle, but we're going to assume that we're moving close to 0 to get the limit. So if we close to 0, we're going to be going pretty much close to 0. Assume that there is an angle here which is equal to 0.000000001, let's say, in radial. But anyway, the only thing that we want to do is we want to show that we want to get the limit as x goes to 0. So we want to do limit as x goes to 0 of the hypo, which is f of x. F of x is the length of the hypo. That is one example, and let's take a look at another. I hope. Okay, what we have here is we have a curve, and we have 2 points, and we have this line connecting these 2 points. So we want to see the slope of the secant. So this is the secant, let's say S-E-C-A-N-T. We want to see the rate of change of the slope as the point Q traces the curve on its way until it reaches P. So it will eventually settle. That means this line will continue to move and change the slope. So we want to find out the rate of change of the slope of the secant. That's what we want. We want the limit. So we want to get the limit as Q reaches P, and that will give us the rate of change of the secant. So let's take a look at the first move. The first move we have, this is what we are going to be doing, is we want the limit as Q moves towards P, but not exactly on P, but towards P. It will be very close, if not almost there. The slope of the secant PQ. So our limit and a function that we're going to do the limit for is the slope of the secant PQ. So here is the first move. Now assume that the secant move to this point, then Q will be right here, and then second move, Q will move. Q is moving with every time we move the secant, Q will be moving. Let's move the secant more. So Q move to this point, and then finally we move the secant, Q move to this. So this is a tangent now. Tangent to the curve. This secant is not tangent. None of them tangent because every one of them crosses this curve in 2 points. The only one that crosses the curve in 1 point is the tangent, and that's why we call it tangent. So all we need is we need to do what? We know that this secant has, we can take, for example, if we want to get it to slope, we have to pull this line and we have to take perpendicular, and then we get, for this line, the tan is going to give us a slope of this one. And you can see that the more we go, the more we increase the angle, what will happen? The opposite will be longer, but the adjacent will be shorter. So they will continue to change. And for this one, the opposite will be even longer and the adjacent will be shorter. And so on. So what we're looking for, it was looking at the rate of change of slope. So to figure it out, we take the limit as Q goes to P of the function that will produce for us the slope of the secant PQ. That's it for this point. Okay, this is the section about limit of a function and limit laws. Pretty much, if we assume that we have L, M, C, and K from the real numbers, then let's define limit f of x as x goes to C, and we say it's equal to L, the constant L, and limit of function g of x as x goes to C equal to the constant M. Then limit of the addition of the two equal to the additions of their limits. limit the subtraction of the two equal to subtraction of the limits. Limit of f of x multiplied by k equals to k times the result of the limits of f of x as x goes to c. Limit the product of f of x multiplied by g of x equal to the product of the limit of the first multiplied by the limit of the second. This is the value of the limit. So limit of the functions multiplied equal to the value of their limits multiplied. Limit of the functions divided equal to the value of dividing the limit of each by the other one, assuming that m is not going to be equal to 0 because we don't divide by 0. Limit of a function f of x to the power n equal to the limit of the function raised to the power n. Limit of the nth root of the function equals the nth root of its limit. Limit of the nth root of a function equal to the nth root of the limit of the function. And of course n is assumed to be even in this case, and we assume also f of x is greater than or equal to 0 because we don't want any 0, anything less than 0, we don't want it under the square. Here not the square root but the nth root. Where n is even, that means we don't need any negative value underneath. That's why f of x must be greater than or equal to 0. And x is an interval containing this c. That's it for the rules, and the rules by practice we will remember them, but they're not really difficult. Polynomial, the limit of polynomials is as follows. This is the general formula for a polynomial. P of x equal to a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 all the way until a sub 0. The last one is a constant. So if we want limit of the polynomial p as x goes to c, limit polynomial p at x goes to c, all we need to do is just replace every x by c. So this will be c, p of c. Instead of p of x, we put p of c. So instead of x, we put c. And then instead of a sub n x to the power n, we put a sub n c to the power n. Just replace every x by c. And that's what will give you the limit. This is very easy for polynomials. Let's give an example. So if I have x to the power 5 plus 3x to the power 4 plus 2x squared plus 1, for example, and this is our polynomial p of x. If p of x is this and we want limit as x goes to c of p of x, it will be what? It will be equal to, according to this one, c to the power 5 plus 3c to the power 4 plus 2c squared plus 1. That's very easy to compute for the polynomials. Now for this theorem, limits of rational functions. If p and q are polynomials and q of c is not equal to 0, then limit of the ratio between two polynomials is equal to the ratio of the limits of these polynomials. Okay, what we want to do is we want to do comparison between these functions. So let's suppose that I'm going to choose a value for x. If I move this way, then I know that for f and for h, this line crosses them. That means there is a point on their domain that is defined for this particular value of x. But for g is out of this domain. G does not have this point in its domain. So first thing I have to do is that any line, I have to make sure that the line passes through all three functions. If it passes through all three functions, then it's good. Now we can see that it passes through g at the end of g, but that's okay. It's still g is part of it. So let's get rid of this one, and keep this as the value of x on this side, and let's go ahead and pick up also another edge. So this is the other side. Okay, so this is pretty much the open interval where all three functions are recognized in this. So from our previous classes, I am sure that you're familiar with figuring out the limit of h of x as x tends to c. And you're also quite familiar of how to figure out the limit of g of x as x goes to c. Obviously, the limit of h of x as h goes to c is equal to L. You can figure it out. This is right here, equal to L. And the limit of g of x as x goes to c is also equals to L. But how to prove that this limit equal to L? We have to first of all prove that if you approach c for h of x from the right, it's going to give you the same value as if you approach it from the left, and that will justify that this limit exists. And same also for the function g of x. Now I'm going to try to do comparison. So let me start with h of x, and this comparison is limited to the common domain between them. So h of x, I can say with a surety that it's greater than or equal to f of x. And I can assure that f of x is greater than or equal to g of x. I want you to look. What does it mean? That means every point on h of x is greater than every point on f of x. And you just pick up any point all the way in this interval, any point in this interval, any value of x in this interval, h of x is greater than f of x except at c. So that's why we said greater or equal to. And in the same interval, every value of f of x is greater or equal to g of x. Say g of x is the least. G of x always has the lowest y value compared to the other two. So that is the equality, that's the inequality that I want. But let me see if I want to do limit on this side as x goes to c, and if I want to do limit on this side as x goes to c. We know that the limit we said is going to equal to L. So we have f of x greater than or equal to L, and also we have here, we have limit h of x as x goes to c is going to give us L. So what if I put a limit here as x goes to 0, as x goes to c, and we'll put also limit here as x goes to c of f of x. Now f of x is sandwiched between two values, L and L, so its limit must be equal to L. And this is what is meant by the sandwich theorem. So the sandwich theorem we can use to prove that limit f of x as x goes to c is greater or equal to L and less than or equal to L, then it must be equal to L. So this inequality implies limit f of x as x goes to c equals to L. That's it. We could go ahead and also continue on the limit and continuities. Let's summarize what we went through, which is now recognized as the sandwich theorem. Suppose g of x is less than or equal to f of x less than or equal to h of x for all x's in some interval shared between all three functions, except for the fact that x should not be equal to c because there is a hole in c. Then we can suppose that limit of g of x as x goes to c equal to limit of h of x as h goes to c at x go to c, and both of them equal, their limit is equal to L. If their limit equal to L, then we can conclude that since they are sandwiching f of x, then the limit of f of x is also equals to L. We're going to go ahead and look at one-sided limit. Over here we have different right hand and left hand limits at the origin. Here is the equation. We have y equals to x divided by mod x. So x divided by mod x, we can write it as y equals to plus 1 if x is greater than 0, and we can write it negative 1 if x less than 0. And from this one we can see that we can write the domain of this function into two ways. The domain, it implies that it's going to go from 1 to infinity for the first case, this case. The first case, the domain is from 1 to infinity. The second case will be the domain from negative infinity to negative 1. So this is for the second case. The second case is this. So this is going to be the domain. Now if we look at the graph, we can see that for the first part, which x greater than 0, to the right of the x, to the right of the y-axis is x greater than 0. So for x greater than 0, not including 0, the domain will be from this all the way until infinity. And likewise, the domain will be from this point all the way until negative infinity, not including minus 1, not including x equals 0. So x equals 0 is not included. What does it mean? We can now talk about the limit on this side. And since we're going to approach the point x equals 0 from the left, so we're going to say limit of y, because y is what we're looking as. Let's say x approaches 0, and then we're going to say from the left, from the right, because plus means from the right, and this is going to be equal to plus 1, because if we approach, we will come closer to 1, 0. So the limit will be plus 1. If we look on this side, then we have to take the limit of y as x approaches 0 from the left. So 0, negative, that means 0 from the left. And this limit will be equal to negative 1. So we can see that the limits are different. The limit as we approach x equal to 0. So the limit as x equal to 0, the limit as x equal to 0, except x equal to 0 coming from the right. And here x equal to 0 coming from the left. So we're coming from the left. And that tells us that the limit does not exist, as we will say. The limit as x goes to 0 in general of y does not exist. Does not exist. We will see this why. But anyway, we're talking about just one-sided limit. So one-sided limit, that means the limit from the right-hand side is available, and it's equal to plus 1. The limit from the left-hand side is also available, and it's equal to negative 1. This is a similar case, but we have a function on this side, which is f of x, and this function, we want to look at limit as x approaches c from the left. As x approaches c from the left, that means x is smaller than c. So if x is to approach c from the left, that means this curve will move towards this end. And when this curve moves toward this end, we know that this end has y equal to m. So if I have to write the point, it will be c comma m. This point in this corner right here, c comma m. So since it is y value is equal to m, that means limit of f of x as x approaches c from the left equal to m. And if we approach from the right, that means we're coming this way, we're approaching from the right. If we're approaching from right, we can say limit as x approaches c from the right of f of x equal to L. Why? Because this point is what? This point is going to be x equal to c and y is equal to L. So this point is CL. And since that is CL, then we know that this limit is going to be equal to L, because the limit is always the value of y. This is the value of y, which is L, and this is the value of y, which is the m. The limit is always the value of y. This theorem basically states that if we take the limit of a function, let's say we call it f of x, as x approaches, let's say, a point c from the left. If that limit equals to the limit of the same function f of x as x approaches c from the right, if the limits are equal, this implies the limit as x goes to c, no sign of f of x exists. That means it has a limit. So let's take a look at the theory. It says, suppose that a function f of x is defined on an open interval containing c except perhaps c itself. That means containing everything except c. And this we can do something like this. And we say that this is the open interval. The open interval, let's call it from a to b. So this open interval containing all the values of x except when x equal to c. So x equal to c is not part of the domain. So if we have to write the domain for this, we can say the domain, it's going to be from the left side, it's going to be from a to c, but c is not included, a is included. And on the right hand side, we'll see the domain over here is this. And this is given by what? This is given by C not included and then B included. So B included right here and C not included, so it's open. Now that we have said this, let's continue. Suppose that a function f is defined on an open interval containing C except perhaps C itself. See, this interval from A to B contains C, but it does not include C in the function because C is not defined. So then what is the conclusion? The function f of x has a limit as x approaches C if and only if there is left limit and there right limit and these limits are equal. So that means if f of x as x approaches C from the left is there and f of x as x approaches C from the right is also there and they are equal, and sure enough they are equal, then that proves that there is a limit for the function f of x as x goes to C, and that limit is also equal to L. One more time, I want to emphasize one point. When we have a point that's not defined in an interval like this point, the function, we cannot say f of x equal to f of c and plug in c because we cannot reach c. But we can say that there is a limit as we approach c from the right, which is by, let's say, c negative or positive. We're approaching from the right. And we can take the limit as we approach from the left, and that is limit as c negative. If the limits are equal, then there is limit for the whole function as we go to c. Not from the right or from the left, we just freely as we go to c, just like this side. Limit f of x as x goes to c equal to L. Why? Because coming from the right, the limit equal to L. Coming from the left, the limit equal to L. How do I know coming from the right? Because we said limit as x goes to c plus. How do I know we're coming from the left? Because we're saying limit as x goes to c negative. So one more time, the fact that we have this point in between, let's say the a and b interval, but it's not included in the interval. It's not included in the interval means what? It's not in the domain. It's not in the domain means what? Means we cannot have a value for f of c. F of c is undefined. Undefined. If somebody asks us to give, for example, f of this point, for example, we can say f of this point is equal to f of this point is equal to f of a plus some constant, I don't know, plus some value. But over here, this point is not in the curve. This point is not included in f, so f cannot define it. We cannot say f of c because c is not in the domain. We've just talked about the domain. C is not in the domain. Okay, let's go ahead and get going. Okay, here it's similar to the one we were just talking about, where we have a hole in the middle. We have a point that's not included in the curve. It's not included in the domain. And in this case, it's not that point, but it is something like this. You can see it in front of us. And then it keeps oscillating on this side, oscillating on this side. And this point, which is x equal to 0, is not included. That's what this one is. So since x or since theta equal to 0 is not included, then we cannot talk about what? Sine theta over theta, because it does not exist. And we cannot say sine 0 over 0, does not exist. But we can say limit as theta goes to, we can write it here. We can say limit of y, which is sine theta over theta, we can say as theta approaches 0 from the right plus. We can say that equal to 1, yes, we can do it. And we can also say limit as theta goes to 0 from the left of sine theta over theta also exists, and it's equal to 1. That's fine. So the two limits are the same. This is equal to this. So that means what? It implies that we can just write freely, not right, not left. We can say limit as theta goes to 0. We can say of sine theta over theta must be equal to 1. Because coming from the right, it's equal to 1. Coming from the left, it's equal to 1. So that means limit as theta goes to 0 of sine theta over theta must be equal to 1. Okay. So this is the conclusion that we just talked about. Limit as theta goes to 0 of sine theta over theta equals to 1. And theta in radii. Let's take a look at this, which is going to prove what we just talked about, which is sine theta, limit sine theta over theta as theta goes to 0. As theta goes to 0. This is limit, we said is equal to 1. And to prove this limit, we can just go ahead and look at the triangle. Let's study one at a time. We want to look at the triangle, which is T A O, where this is T, this is A, and this is O. So this triangle, if we want to get the triangle's area, we're going to go through this. This is what? This is the height, and this is the base. So we know that the area of the triangle is half the height times the base. So the height is tan theta, and the base is 1. So multiplied by 1 divided by 2. That's the area of the larger triangle. Now let's take a look at the area of the smaller triangle. the smaller triangle is the triangle defined by P and Q and O. P and Q and O. Here is P, here is Q, right here, and here is O. So we can say that this is the height, which is equal to sine, and this is the base, which is equal to cosine. So we can say that the area of this is sine theta multiplied by cosine theta divided by 2, because the base times the height divided by 2, that's the area of this. Now we will look at the area of the sector. The sector is, we're going from P sector, which is curve. So for this curve, we're going from P and then to A and then to O. That means we're looking for the area of this sector. This is a sector. Okay, we want to look at the area of this sector. Okay, the area of this sector depends on the ratio of the angle, okay, and the ratio of the angle is as follows. The angle is theta. Since the angle is theta, we can go ahead and relate theta in ratio to the overall angle of a circle. The overall angle of a circle is 2 pi, and theta is this angle. So the ratio of this angle with respect to the overall circle is theta over 2 pi. Theta over 2 pi. Now, if I want the area, then the area I'm going to multiply by the area of the circle, which is pi r square, the area of the circle. But I know that r is equal to 1. Radius is equal to 1. Here is the radius. Radius is equal to 1. So I can just say that the area of this sector is going to be pi goes with pi, r is equal to 1. It's going to be theta over 2. So I have 3 areas. Now let me go ahead and write down the 3 areas. The first area, we said it is tan theta over 2. The second area is the middle for the sector, which is theta over 2. The third area is the smaller triangle, which is sine theta cosine theta, sine theta cosine theta divided by 2. Now, which one of the 3 is the largest? Of course, the largest is the area of the bigger triangle, TAO. So TAO has an area of tan theta over 2, so we'll say this is greater than the one in the middle. And the one in the middle is the sector, the one with the zigzag line. The zigzag line here. The sector is smaller than the bigger triangle, but it's larger than the smaller triangle. So we'll say theta over 2, and this is greater than the area of the smaller triangle. Okay. So the last one is the area of the smaller triangle. I'm going to shade the smaller triangle to show this area. So here is the smaller triangle. Its area is half the base, which is cosine, times the height, which is sine. Cosine times height divided by 2. Okay. And the sector, we said it depends on the ratio. The ratio is theta over 2 pi, where theta is this angle relative to the angle of the circle. The angle of the circle, since the circle is something like this, the angle of the circle is 2 pi. Or you can say the radius of the circle, the circumference of the circle. But the angle, this is 2 pi. If we go one of them, this is like half pi, 1 pi. And if we go 1/4, this is what, pi over 2. So this is pi over 2. So we can relate the angle. So this is the relation of the angle, and these are the ratios. This is the area of the bigger triangle, and this is the area of the sector, and this is the area of the smaller triangle. the smaller triangle, this one. Now let's go ahead and do the math and come up with a proof for the point that we just talked about, which is limit of sine theta over theta as theta goes to 0. So I'm going to rewrite this. So I have what? I have tan theta over 2, and I have it's greater than theta over 2, and I have this is greater than sine theta cosine theta over 2. Now if I multiply by 2 both sides, I'm going to get what? I'm going to get sine theta cosine theta is less than theta is less than tan theta. If I divide every one by sine theta, I divide this by sine theta, and I divide this by sine theta. What I'm going to get here from the left hand side, I'm going to get just cosine theta, because sine theta could be cross this one with this one. Sine theta crosses sine theta, and the middle I'm going to get theta over sine theta. And in the other side, I'm going to go 1 over cosine theta. You can review that, because tan theta is equal to sine theta over cosine theta. When you divide by sine theta, we get 1 over cosine theta. Now, what we're going to do now is we're going to go ahead and flip each term. So I'm going to say 1 over cosine theta. Okay, this is going to be flipped also. It's going to be greater than sine theta over theta, and this is going to be greater than cosine theta. I flip them. Now let's take limit of cosine theta as theta goes to 0. That's equal to 1 for sure, because cosine 0 is equal to 0. And since that is the case, limit cosine theta as theta goes to 0, that means I will have this will be equal to 1. Okay, and in the middle, we're just going to put what? We're going to put limit as theta goes to 0 of sine theta over theta. That's in the middle. And then on the other side, we're going to put what? We're going to put 1, because we know that limit of cosine theta, we just proved that limit of cosine theta equal to 1. So 1 over limit cosine theta will give us 1. So now what we have is the following. Let me just put it right next to it. We have 1, and then we have limit of sine theta over theta as theta goes to 0, and then we have 1. Let me write it in a horizontal way. So we have 1, and then this is greater than limit of sine theta over theta as theta goes to 0, and then we have greater than 1. Since this says 1 is greater than limit sine theta over theta as theta goes to 0 and greater than 1, then it's obvious that limit of sine theta over theta as theta goes to 0 must be equal to 1. And this is proved by the Sandwich Theorem. So this is just like the Sandwich Theorem, proof of the result that we just also proved in a different way. Let's take a look at